This is the general hierarchy. You can see that quality specifications specific to clinical outcomes are at the top of the hierarchy, and goals derived from current state-of-the-art are at the bottom. This does not mean that goals based on the current state-of-the-art have no value. It's just that the other types of goals have more value. Let's look at the 5 parts of the hierarchy in more detail. Goals that are specific to a clinical setting should be used before anything else. A quality requirement for very precise monitoring in a transplant patient should take precedence over a general regulatory-based requirement. For general clinical settings, 2 main types of quality specifications are recommended. Quality specifications derived from biological variation and those based on the analysis of clinicians' opinions. The basic idea behind quality specifications derived from biological variation goals is to ensure that a shift in a test can be detected. We need to keep the analytical variation significantly smaller than the inherent biological variation of the test. Another approach is to interview treating clinicians and ask when they would consider a change in a result significant. Ultimately, this allows the construction of a set of quality goals. Unfortunately, this approach is very time-consuming, and the results vary from clinician to clinician. Next in the hierarchy are recommendations from experts and professional organizations. These are preferred to performance goals derived from regulatory agencies and external quality programs. The least preferable type of quality specification is derived from the current state-of-the-art. Current state-of-the-art generally refers to the median performance of a group. State-of-the-art is not related to the clinical settings. It simply focuses on identifying what the average quality of a test is. Half the laboratories in a given group will have higher performance. Goals may be expressed as a percentage, or a concentration, or a number of standard deviations. Examples might be plus minus 1 millimole per liter, or plus minus 3 standard deviations from the mean. If the goal is not a percentage, it must be converted to a percentage by dividing it by the target value and multiplying by 100. Each quality goal specifies some allowable distance from the target value. The target value is usually either a group mean or the mean of the control lot. In the United States, the CLIA laws form a set of quality specifications derived from a regulatory body. An example from CLIA is the platelet specification of plus minus 25%. For a group of laboratories evaluating the same specimen, each lab should report a value that's within 25% of the group mean. One of the deficiencies of most quality specifications derived from regulatory bodies is that there's little science behind the specification. Why is the US CLIA value 25%? Why not 24%? A more scientifically sound approach is to derive quality specifications from medical requirements. However, there's no universal agreement on what the medical requirements are. Biological variation is an approach that uses the within-person variation and between-people variation of the analyte in question to derive the maximum amount of analytical error that can be tolerated without adversely affecting the value. For platelets, the within-person variation is 9.1%, and the between-people variation is 21%. It can be probabilistically computed that as long as the analytical response is within 13.4% of the target value, it will not have an adverse effect on the result. Dr. Carmen Ricos and her associates have determined the components of biological variation for about 200 analytes. For all of your laboratory QC needs, go to www.qcnet.com.